Cations are smaller than their parent atom because they shed their entire valence shell, and also now there's more protons than there are electrons. So the protons can pull a lot tighter and bring those electrons a lot closer in. Anions get bigger because they gain electrons, and now there's more electrons than protons, and so the protons can't pull on them as tightly. And so in general, the cations are about half or even smaller of the size of the original atom, and anions are usually twice as big as the original atom. Again, magnesium wants to give up 2 electrons to become like a noble gas. It's 1s2, 2s2, 2p6, 3s2. If it gives up 2 electrons, it'll become just like neon. And chlorine each wants to gain 1 electron to become like argon. But you need 2 of them to gain the 2 electrons. So magnesium chloride has to be MgCl2. Magnesium gives up 2 electrons to be like a noble gas. Chlorines are gaining 1 electron each to become like a noble gas. But everyone wants to be like a noble gas. Aluminum loses 3 electrons to become like a noble gas. Oxygen gains 2 electrons to become like a noble gas. So here, aluminum will lose 3 and fluorines will gain 1. You need 3 fluorines to accept the 3 electrons from 1 aluminum, so AlF3. But the net goal is for everyone to be like a noble gas. And so in aluminum fluoride, all 4 of those ions have the electronic configuration of neon. In almost all stable compounds, the atoms are attempting to gain noble gas-like configurations. So barium sulfate, barium's in group 2, it'll give up 2 electrons to become like a noble gas. Sulfur's in group 6, it'll gain 2 electrons to become like a noble gas, BAS. So what is the formula for potassium phosphide? Potassium's in group 1, they'll give up 1 electron to become like argon. Phosphorus is in group 5, it'll gain 3 electrons to become like argon. So you need 3 potassiums and 1 phosphorus, because each of the 3 potassiums gives up 1 electron and the phosphorus wants to gain 3 electrons. And in the end, they all have the electronic configuration of argon. They're all like noble gases. Sodium sulfide. Sodiums want to give up 1 electron to become like neon. Sulfurs want to gain 2 electrons to become like argon. You need 2 sodiums for 1 sulfur. But in the end, the sodiums have the electronic configuration of neon, and the sulfide has the configuration of argon. Everyone is like a noble gas, so everyone is happy. What is the formula for magnesium nitride? Magnesium will be +2, nitrogen will be -3. They both go into 6, so 3 magnesiums is +6, 2 nitrogens is -6. Now, the ionic bonds only work when you have a metal and a nonmetal, because the metals will give electrons, and the nonmetals take electrons. And that works. When someone will give and someone will take, it works really well. But when you have only nonmetals, or a nonmetal and a metalloid, there's no one to give, and everyone wants to take. So the best you can do is share. Because again, hydrogen wants 2 valence electrons. But no one will give it any electrons. So they share. And in a shared electron, in the shared bond, they both grab those electrons and they both claim them as theirs. So imagine you're holding a pop bottle, and someone else grabs onto the pop bottle. As long as both of you refuse to let go of the pop bottle, you're both bound to each other. And that's exactly what a chemical bond is. Both atoms are holding onto those electrons and saying it's theirs, and because both atoms are grabbing onto the electrons and refuse to let go, they're bound together. So same thing with chlorine. Chlorine would like 8 electrons to be like argon. If there was a sodium, it could just steal 1 and be happy. But there's only 2 chlorines. There's no one to give. Everyone wants to take. And so you get a covalent bond. And again, each chlorine is claiming 8 electrons, 6 of its own and 2 shared. The shared ones get double counted. Both atoms think it's theirs. And that's what holds them together. They're both grabbing onto those electrons and refusing to let go. Likewise, if you and someone else grab onto something and refuse to let go, you're stuck together. And that's exactly how a chemical bond holds them together. However, sharing is not the same as having something to yourself. And so chloride minus is extremely stable. And like sodium chloride, that'll last for thousands of years. Chlorine gas, while stable enough to isolate and bottle, is still a pretty reactive chemical. And so again, when we say the word stable in chemistry, what we mean is stable enough to isolate and bottle it and sell it. If you can trap it and bottle it and keep it, it's stable, even if it's still reactive. So it's a relative term. Another way to draw shared electrons is with the chemical bond dash. This dash represents 2 shared electrons. So each of these fluorines has 8 electrons now, 6 of its own and 2 shared. You can share more than a pair. So in oxygen, you have a double bond. Each oxygen has 4 of its own electrons and 4 shared. With nitrogen, we have a triple bond. Each nitrogen has 2 of its own electrons and 6 shared. They each claim 8 electrons, though. That desire to have 8 valence electrons, like a noble gas, is a strong driving force of chemistry at this stage. Sometimes electrons are shared, but they're not shared equally. And that leads us to the polar covalent bond. And then we're going to have partial charges. In a polar covalent bond, one of the atoms that has the chemical bond is hogging the electrons. So the electrons spend most of their time around one of the atoms, and because electrons are negatively charged, that atom becomes partially charged. Not a full -1, but some partial negative charge. And so that is the small Greek letter delta, which signifies a little bit of negative charge. Whereas this proton in this hydrogen doesn't get to see its electrons very much, so it's partially positive. And that's a dipole bond. We have the electronegativity scale to let us see how electrons will be shared. It was developed by Linus Pauling. And electronegativities go up as you go up a group and as you go right across a period. So fluorine is our most electronegative element. Electronegativities only apply to the shared electrons in a covalent bond. And that's why you don't see the noble gases there, because noble gases don't share electrons. They don't form compounds, and so they're not in this. Electronegativities only apply to shared electrons in a covalent bond. And you take the 2 electronegativities of the 2 atoms involved in the bond. If their differences are 0.5 or greater, you have a polar covalent bond. You have partial positive and partial negative charge. If the electronegativity difference between the 2 atoms in the chemical bond is less than 0.5, if it's 0.4 or less, then you have a non-polar covalent bond. The electrons are shared equally and there are no partial charges. So ionic bonds are always a metal and a nonmetal. Covalent bonds, you have 2 nonmetals, or a nonmetal and a metalloid, and the electronegativity difference between the 2 is less than 0.5. If the electronegativity is greater than 0.5, or 0.5 or greater, we have a polar covalent bond, and we do have partial charges. So the carbon-sulfur bond, they each have an electronegativity of 2.5. The difference is 0. Nonpolar bond. Nitrogen-chlorine bond. Electronegativity difference of 0. So nonpolar bond. Phosphorus-oxygen bond. Oxygen has an electronegativity of 3.5. Phosphorus has an electronegativity of 2.1. The difference between the 2 is 1.4, which is 0.5 or greater. Now we have a polar covalent bond. And we can signify that with the arrow signifies the negative charge, and this slash here kind of makes it look like a positive sign. That's the positive side of the bond. Same with nitrogen and carbon. There's a 0.5 difference in electronegativities. And again, the only place you can find electronegativities is on this chart that was developed by Linus Pauling. So whenever you have to look up electronegativities, come back to this chart. A polar covalent bond will form between which 2 atoms? Well, it can't be A because that's a metal and a nonmetal. That would be an ionic bond. C would be an ionic bond too, metal and a nonmetal. D, fluorine is 4, but so is fluorine. Oops. So the difference is 0 between 4 and 4. So it has to be B. In hydrogen chloride, as long as it's not dissolved in water, you have an intact covalent bond. And the electronegativity difference is chlorine is 3, hydrogen is 2.1, the difference is 0.9. And so you'd have a polar covalent bond. A molecule can contain polar bonds and still be nonpolar depending on the geometry of the molecule. So like carbon dioxide, the carbon-oxygen bond is very polar. So the oxygen is pulling really hard on the electrons, but there's 2 of them. And they're exactly 180 degrees apart from each other. And so in the end, this ends up like being like tug of war. If you have 2 sides that are pulling just as hard, no one goes anywhere. It's like no one's moving. 2 equal but opposite forces will cancel each other out. If the bonds are asymmetric, then you will end up with a polar molecule.